how do you show? Remember, I had these approximates. There was C1 and C2 is this one and C3 is this one, and so forth. They're all continuous functions. Why do they converge? Why do they converge? Is the convergence monotone pointwise, by the way? Why? No. Yes. No. Well, this is part of C1. C2 does that. Drops down. This value for C2 is lower than for C1. So there's a little bit of vibration there. But once you get past a flat spot, nothing ever changes. Right? C1. I mean, all of these approximates for any n, the middle third looks like that. It's 1/2, no matter what. And once you get past C2, 1/4, 3/4 looks like this. So anyway, what you have to establish is the uniform convergence of the approximates. What will do it for you? If you can show, given epsilon greater than 2, if there exists an n of epsilon such that if m and n jointly exceed n of epsilon, then you are assured that the mth one minus the nth one is less than epsilon. Then you can say that the uniform convergence criterion, Cauchy style, guarantees the convergence to be. Okay? If that's true, then Cauchy's uniform convergence criterion is satisfied in this. All right. Burke says this: Cn minus C sub n plus 1 is less than or equal to 1 over 3 times 2 to the n plus 1. Okay? How can I use this to prove that? A little practice here. This is midway down page 69 here. We are still trying to explore the Cantor function. We've integrated it. That was fun. We've defined it, integrated it, looked at the approximates, and now we'd like to really show that our assumption that we could integrate it is valid. We said it's continuous. So the Cauchy integral exists. Now we're backing up and sort of proving it. Okay. If you need to show the Cauchy condition, and you have the condition between two adjacent values, what do you suppose you do? You know, you can do the Cm of x. Let me drop the x's. There's no x over here, so this is uniform for all x on A B. If I have Cm minus Cm plus 1 plus Cm plus 1 minus Cm plus 2 plus Cm plus 2, blah, 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 plus, minus. At the very end, I'll have C n minus 1. I'll have added that. See, first I'm subtract, add, and then finally take away that. Right?
Right.
Okay, so I've added, subtracted a bazillion of these things. By the generalized triangle inequality, absolute values outside is less than or equal to what? The individual terms, right? All the way to the bitter end. True. And can we write that as a sum? I would like to go let's see. So K starts at M and goes to N minus 1, right? All right, now we have Cm of x minus Cn of x for all x in AB is equal to this big monster thing, which is smaller than the sum of the monster things. So it's smaller than this sum. If we can control this sum, we've got this thing controlled, and then we can conclude that the convergence is uniform, right? So how do we get a handle on this? Well, look, he tells us that the difference between two of the adjacent ones is this thing is equal to 1/3, or it's actually less than or equal to 1/3 times 1 over 2 to the higher power, right? K plus 1. True? So this thing itself is less than or equal to 1/3. 1/3 is uniform throughout, so I go from K equals M, N minus 1. 1 over 2 to the K plus 1. Why don't we do this? I'm going to put a 2 there and take it out of there. Wait a minute. Put it down here. Put it in the wrong place. Okay. So this thing is 1/6. This is bigger than the sum we're trying to show is this. All right, now Rob likes these geometric series. If I start here and stop there, how big is this? Well, look, here's a little trick that analysts use to make these things easier. These are all positive terms. What if I just let that go to infinity? Right? Still true. But now, you don't have to deduct the n minus first term out here, right? It's just equal to 1/6. The first term is 1 over 2 to the m, right? Divided by the constant ratio, which is 1/2, 1 minus 1/2. So, what is that? It's equal to 1/6 times 1 over 2 to the n minus 1, right? Okay, as m goes to, if we want to make this smaller than epsilon, can we find an m so that once we get beyond it, this is true? I mean, this thing has to be less than epsilon. If that's less than epsilon, this is less than epsilon, convergence is uniform. So tell me, what should epsilon be if 1/6 times 1 over 2 to here, what should m be if that's true? If that's true. So 1 over 6 epsilon is less than 2 to the n minus 1, right? So take the binary log, LG, of 1 over 6 epsilon, so that's minus the binary log there, is equal to m minus 1. So m has to be greater than, take the 1 over this side, 1 minus binary log of 6 epsilon. Found an m. That works. So if I pick m and n bigger than this guy here, so he becomes the n of epsilon, where if m and n are both bigger than him, then the difference is less than 3 sine epsilon. And that establishes the convergence theorem. It's uniform. Right here. You see what I did? I took the log base 2, and logs don't disturb the order, right? If x is greater than y, then log x is greater than log y, no matter what base you're talking about.
Yeah, so I was just going to say, I like to take next one.
Yeah.
I don't have a log base 2.
Oh. This is pretty much just formal. I think you could probably stop here and just say, yeah, I can make an m big enough so that's true. K. So that nails that one down. And then Rob's going to integrate X times the Cantor function from 0 to next week. Somebody remember that because I'll forget.